We will now look at what composite functions are, the conditions for the existence of composite functions, and how to determine the domain and range of a composite function. So, what is a composite function? Earlier, we have learned that a function is a single machine that converts some input into some output. Now, imagine taking the output of this machine and putting it into a second machine. We will end up with a secondary product. When an input undergoes two or more successive transformations through some functions, the series of transformations is collectively termed a composite function. So if we start from x and we undergo a certain transformation through the function f, we will end up with fx. And now we are going to use fx as an input into a second function g. So it becomes g of fx, which we can write as gf of x. Thus, gf is a composite function where the input x is first transformed by function f, then followed by function g. And of course, there are conditions that must be satisfied in order for a composite function to exist. Now, imagine our first function is a recycling factory which can turn iron parts into molten iron and plastic bottles into plastic beads. And the second factory is a metal working company which produces metal screws. If we were to take all the output from the first factory, i.e. raw iron and plastic beads, into the second function, there will be some problems. Because the second factory cannot process the plastic materials given by the first factory. Therefore, there will be a breakdown of the manufacturing chain. So we know that for the manufacturing chain to work, the first factory must be able to process whatever output that is given by the first factory. This means that the set of output given by the first factory must be smaller than the set of input that the second factory is able to take in. Therefore, for a composite function gf to exist, we have to satisfy the condition that the range of f is a subset of the domain of g. Let's take a look at some examples now to determine if a composite function exists. In example 1a, we are asked to determine if the function fg exists, and f and g are given as such. So in order for composite function fg to exist, the range of g must be a subset of the domain of f. We can easily show that the range of g will be equals to 0 to infinity inclusive of 0. And now if we compare the range of g with the domain of f, we can see that the range of g is not going to fit inside the domain of f because over here there is an extra 0 value which is not found in our domain of f. Therefore, we can say that the range of g is not a subset of the domain of f, which means that the composite function fg does not exist. Now, if we change the definition of g from x squared into x squared plus 1, the range of g can be found to be from 1 to infinity inclusive of 1 now. And if we compare it with the domain of f, which is still from 0 to infinity, we can see that the range of g now is clearly a smaller set as compared to the domain of f, which means that the range of g now becomes a subset of the domain of f, and therefore we know that the function of fg, it must exist. After proving that a composite function exists, we can then proceed to find its definition. Using this example to find the composite function gf, what we have to do is to first find fx from x, following which we can substitute the expression of fx into gx, and this resulting expression is the definition of gf. In short, what we can also do is to simply say that for gf, gfx is the same as g of fx, which is the same as g of x squared plus 1, which therefore gives us ln of x squared plus 1. Next, we have to define the domain of gf as well. The domain of gf is the same as the domain of f, as given in this relationship over here. This is because no matter how many factories there are in the line, the end product is always dependent on what is the input of the very first factory. And therefore, I know that the domain of the composite function gf will be equals to the domain of f, which is therefore equals to everything from minus infinity to infinity, and therefore I can write down gf in similar form to be ln of x squared plus 1 for all real values of x. In this example, we are asked to find out the value of k and a such that the composite function gf exists. So we know that for composite function gf to exist, the range of f must be a subset of the domain of g, and therefore I can force the range of f to be exactly the same as the domain of g. So range of f is going to be equal to 3 to infinity excluding 4. So what is the corresponding domain of f that gives us a range of 3 to infinity excluding 4? Let's find out using the graph. The graph of y equals fx looks like this, and the graph of y equals to 3 is over here. And what we want now is the y values to be more than 3, and it has to exclude the point 4. So this is y equals to 3. This point over here is 4. So we need to find out what is the corresponding domain, which is this, excluding this point over here. So let's find out what is the corresponding domain for y equals to 3. So we have x squared plus 2x equals to 3, x squared plus 2x minus 3 equals to 0, which means that x plus 3, x minus 1 equals to 0, and x equals to minus 3 or 1. Next, I'm going to solve for this point over here. So x squared plus 2x equals to 4, x squared plus 2x minus 4 equals to 0, and for this I have to solve using the quadratic formula to be x equals to minus 2 plus minus square root 2 squared minus 4 times negative 4 over 2, and this gives me negative 2 plus minus square root 20 over 2, or negative 1 plus minus square root 5. And of course, what we are interested in now will be the positive values over here from 1 all the way to infinity, and this point corresponds to negative 1 plus square root 5. Therefore, the value of k must be equals to 1, and the value of a must be equals to minus 1 plus square root 5. To find the range of a composite function, there are two ways we can do it. The first method is a more direct way of finding the range, that is to simply find the definition of gf, then obtain the range by drawing its graph and determining the range graphically. However, this method is more restrictive as it will only work if all the expressions and domains are well defined such that we can obtain the graph using the GC directly. In example 3, we will use the graph method to determine the range of the composite function gf. So let's first define the function gf. So I have gf(x) equals to g of x squared plus 2x, which therefore gives me ln of x squared plus 2x plus 2, and the domain of gf follows the domain of f, which means x must be more than or equals to negative 1. Now, in order for me to find the range of gf, I will have to draw the graph of gf, and the graph of gf looks like this, where this point is minus 1 and it cuts the x-axis. And therefore, from this, I can see that the range is going to be from 0 all the way to infinity, and therefore the range of gf will be equals to 0 to infinity inclusive of 0. The second method is called the mapping method. It is a little more complicated, but it will be more robust. Basically, it works by finding out the range of the composite function in a stepwise manner. For composite function gf, we start with the domain of f, then we determine the corresponding range of f. This range of f now becomes the input of g. Thus, we will need to change the domain of g from what is given in the question into this range of f. And finally, based on this new domain of g, we will be able to find out the corresponding range of g which will be the range of GF. In example 4, we are now unable to draw the graph of y equals to gfx on the GC as there is an unknown k in the equation. So let's use the mapping method to find out the range. For gf, we will start from the domain of f, which is minus infinity to infinity. This will give us a corresponding range of f, which if we evaluate based on this expression after completing the square, we will get k minus 1 to infinity. Now I'm going to force the domain of G to be equals to this range of f, and I'm going to call this new domain of G new, and therefore it becomes k minus 1 to infinity. Now based on this new domain of G, I can find out the corresponding new range of G. So range of G new, it will be how much? It will be, if we draw the graph out and k minus 1 is over here, it will be this portion over here, which means that the range will be from minus infinity all the way until negative e to the power of k minus 1. And this value over here will be equals to the range of GF. And I can say that range of GF therefore equals to negative infinity all the way to negative e to the power of k minus 1.